So welcome to the Winds and Currents webinar. Today we're fortunate to have Ernesto Rodriguez, who's going to talk about what current does a Doppler scatterometer measure, and talk about lessons from the S-mode experiment. So go ahead, Ernesto.
Okay, thank you, Sarah. And I've made a lot of pictures in here, so hopefully you've minimized the amount of text and equations, but there are a few. And I try to be a little bit provocative because I'm often confronted by all these people who tell me they know very well what is being measured, but don't always know exactly what's being measured. So we're trying to understand what's being measured with a Doppler scatterometer called Doppler Scat. And we've been deploying it as part of something called the S-mode Earth Ventures suborbital campaign, which is a NASA mission. Tom Farrar is a PI. And a lot of the effort that is going to be presented here is the work of many, many people. And I've just listed a few of them that have contributed key things to this presentation. So I won't go through everybody here, but there's a mix between a variety of instruments and capabilities. So I'll put this up at the end so you can see who it is. So here's my experience talking to theoretical scientists. They say they measure sea surface height, and that's a very mature technique. And when we say that, what we really mean is that we're measuring the centroid of specular point reflections distributed over gravity waves and influenced by winds. And going from that specular point centroid to sea surface height has taken nearly 40 years or more. And there are still corrections that are trying to be understood. So far, there's no quantitative theoretical prediction, although there are many qualitative theories that say what the data should look like. Similarly, scatterometry has been around forever, and we say that we measure neutral winds, but what we really mean is that we measure the amplitude of capillary and capillary gravity waves plus wind breaking as it affects the radar backscatter cross-section. And turning the radar backscatter cross-section into neutral winds has been going on also for about 40 years. And also, there's no accurate quantitative theoretical prediction, although there are improving qualitative ones. And yet, both of these measurements are used throughout the community by people who have forgotten the pain of what it took to get there. So the purpose of this talk is to try to say what we mean when we say we measure surface currents, at least with the Doppler scatterometer. So the Doppler scatterometer that I will be talking about is something called Doppler Scat. It's a JPL instrument. Dragan Perkovic-Martin is the PI. And it works in a very simple principle that's used in many other ocean sensors. It sends out a pulse, and a very short time afterwards, it sends out another pulse, and then it can measure the phase difference between these two pulses. And you can relate that phase difference to a change in range between the sensor and whatever is scattering, little red balls in this case. And so you can turn that, divide that range change, divide the time that it took to go from one place to the other, and call that a radial velocity. And then you can do that for multiple azimuth angles, and then you can retrieve a vector out of it. And this is a technique or a principle that's used in ADCPs. It's used in HF radar. But the innovative part about this is that it can be deployed from space. It can be scaled to something like Odyssey, can have a very large swath. So it can measure, in the airborne case, on the order of something like 100 kilometers by 50 kilometers in 3 hours or so. So it has a lot of promise, but it's also not clear what it is that we're measuring, because the radar is sensitive to Bragg waves. These are resonant waves. They have an intrinsic speed of about 31 centimeters per second. So we can at least expect to subtract that out from the currents. They're, of course, affected by the currents, but they're also generated by other waves. When you have high curvature, you have parasitic capillary waves that are generated by these other waves. So we need to subtract the velocity from these other waves as well. They're modulated by surface currents, but also they suffer from some Lagrangian flow. And there's an additional Stokes drift component and surface drift component that goes into it. And then finally, most of the velocity, or the vertical velocity, is due to larger gravity waves, and we need to be able to subtract that out. So the challenge here is how to do that and remain with something that's sensible. And so the velocities that we need to subtract out are the free Bragg resonant wave. So if that were the whole story, it would be very easy to subtract out, because you have the dispersion relationship. The radar resonates with just one wavelength. And so if you turn that dispersion relationship into phase speed, you get about 31 centimeters per second. You subtract that out, and then you're done, except you're not, because as you see in this beautiful picture on the right, very frequently in the ocean, you get high curvature events like this, generating parasitic capillary waves that travel at the same phase speed as the waves that are generating them. And so there's no single resonant wavelength that generates these parasitic capillary waves, even though they have Bragg components. So there's a whole range of wavelengths, which I've normally put, things that have the higher curvature will have the most of these. So somewhere between 10 centimeters to a meter, but it could be larger. And if you look at the phase speed of those waves, it's much larger than the phase speed of the free Bragg resonant wave. And it's been known now for a while that these capillary waves, that these bound capillary waves, are pervasive in the ocean. They've been observed using optical polarimeters and dispersion relationships. They've also been part of the wind geophysical model function models lately. So we know they're going to play a role. In addition to that, as these waves ride on top of the bigger waves, the signal, the strength of the signal is weighted by how bright that part of the wave is. And the waves are not uniformly bright. They change brightness for a large reason. So here, schematically, I have a large-scale wave, and it's the wind and wave direction are going to the right. And what you have, due to the fact that the waves are nonlinear, is going to be a hydrodynamic modulation of the small waves by the large waves. And typically that'll change the amplitude of the small waves as they ride along the large waves, with a larger amplitude being towards the crest, a little bit forward of it, and the lowest amplitude being towards the bottom, but a little bit to the right of it. So if that were the whole story, then you would have a brighter return from the top than from the bottom. And the radial velocity is symmetric for this wave. But because there's a brighter return from the top than from the bottom, it would not cancel out. So you would have a significant radial component added to the velocity. In addition to that, what is making it even more complicated is that the backscatter cross-section depends on the incidence angle, and the large-scale waves modulate the incidence angle. So if we're looking from the right over here into the wave, this part of the wave will face the radar more strongly than this part of the wave. And so this also will be brighter than that part of the wave. So if you put both of these things together, you get a sort of picture that looks like this. You have the brightest part of the wave being not at the peak, not at the trough, but somewhere around the middle. And it is not symmetric with the darkest part. So we should expect that the radial velocities do not cancel out from the large scale waves. So that's going to be something else that we need to take into account. And in principle, we do not measure large scale waves with this instrument. So one of the questions is, would we have to additionally measure the large scale waves and at a high resolution to figure this out? And part of the answer to that is no, we don't think so. And I'll try to convince you of that, because the modulation is largely due to the steeper part of the waves. And the steeper part of the waves are due to the wind-generated waves. So if the waves are somewhat in equilibrium with the wind, we can expect to be somewhat consistent in the level of leakage that you have from the large scale wave into the small scale wave, into the radial velocities. But we need to take that out for sure. So this is a simple equation of what you would have to do to derive the theory of what you're measuring. You would have the advection by the current, and which current is, of course, one of the things that we need to talk about. But you would have to also subtract the portion that is due to free Bragg waves and the portion that is due to the bound Bragg waves. And these also, in addition to having their own speed, they also have an angular distribution. There's also the contribution to gravity waves, which also have a variety of speeds and angular distributions. Wave breaking also will give you some return, because the foam itself and the roughness generated by that has a speed. And there's because the waves are modulating it up and down, and you're taking a spatial average, you actually get half of a Stokes Lagrangian drift into this. And there are other effects that I haven't mentioned. So, you know, I and others in the community have tried to come up with models like this. And I hope that we'll hear later on from the group at Ifremer that are working on a model like this. But it's a very complicated model, and there are things that are still uncertain. So in order to make progress, I've just taken the bull by the horns and just said, well, the difference between what we measure and the true surface current is some unknown function, which I'm going to call F sub S. And we're going to assume that it's a function of the neutral winds and a function of the direction relative to the wind direction. And that's a very bold assumption. We have to see whether it's right or not. And furthermore, to make it tractable, and also because it seems to be a good fit, we're going to assume that it's parameterized by very few parameters. There's a constant factor. There's a factor which is I call C1, which would be the radial velocity of something that was purely acting like a vector. And then there are other higher contributions due to the fact that the angular distribution of the waves in the ocean is not that of a pure velocity. And so you have to correct for those. But I only go up to third order harmonics. That seems to fit the data fairly well. There are other theoretical approaches that have been taken. So there is something called Doppler that has been made in Europe. The first version of this Doppler started in 2005 with Bertrand Chaperon and Fabrice, and then it's been elaborated since, and it's still being elaborated. There's been a semi-empirical approach by a group that also included Bertrand, but it was led by Yuri Yurovsky in Crimea. And then there is the group that we at JPL have, the approach that we've taken is that this bold, barefaced approach that just go purely empirical because we're not sure how to model all this other stuff. So as with any of this purely empirical approaches, it only works as well as you have data for it. And initially we had some guesses about this, but the ESMO campaign has been really a boon for trying to understand what that empirical function should be. So the ESMO campaign is a very large-scale campaign. We start our last month-long experiment data collection next week, and it deploys, in addition to the Doppler Scatterometer instrument, an SST instrument, another instrument called Doppler in mass, which is from Scripps, which measures the surface currents as well, some ocean color instruments, and a wealth of assets in the ocean that can measure both currents and winds that we've used for training. So the most important ones so far have been sail drones and wave gliders. So in the last experiment, we've had 4 sail drones, 8 wave gliders, and they provide ADCP, SST. They also have meteorological data sufficient to invert for neutral winds. And the main disadvantage that they have, or advantage, is that they have their downward-looking ADCPs. The first spin that we can measure reliable happens at 4-meter depth. And so we take that to be the reference, and really it is at least this deep what we're trying to measure from space in the Odyssey mission. So we'll take that to be truth. We also have other sensors, 2 other sort of sensors. There is the Cartha surface drifters, which are basically passive devices that try to be as neutrally following the 40-centimeter currents, integrating over this drogue over here, have been extensively used during the Cartha experiment and also by us, and have a long history by now. And there's a new instrument called Doppler from Scripps that uses the dispersion relation from gravity waves. So they take movies and they cross-correlate the movies. They take Fourier transforms of these space-time movies, extract the dispersion relationship, and from the Doppler shift to the free wave dispersion relationship, they can estimate the current at various depths. And so here, courtesy of Luc Lenin, who is the PI for Doppler, is some ADCP currents up to about 4 meters, and the Doppler currents as inferred as a function of depth. So far, and to the right is the level of validation that Doppler has against wave gliders. So you can see a pretty good correlation between them. You can also see potential issues that we may have to address in the future. One of them is that between 4 meters over here and the surface, there can be substantial shear. So that's something that we need to find out whether that's going to be a systematic problem and how much of that shear is going to be getting to the 4-meter estimates that we're going to try to do. And you can also see that because the ADCPs and the wave gliders are using the nearest range, and sometimes there's some contamination, and we see some disagreement between the two of them. But anyway, all these things have some usage in the community and some heritage, and so we'll be using them as part of the training. Now, we have had two campaigns for the S-mode experiment. One we call the pilot, the other one the intensive operation period 1. In total, we had about a month and a half of data collection, which allowed us to get a whole lot of data. It's not large-scale data in the sense that ChatGPT has, but we have on the order of 20,000 collocations. So it's a substantial amount of data between the Doppler scat data and these other instruments. So during that time, we sampled a variety of ocean conditions. So here's a histogram of the wind speed on the bottom and number of observations on the top of significant wave height over here, as measured by the sail drones or the wave gliders. And I put in as a reference line the Pearson-Moskowitz prediction for well-developed seas. So if everything were wind-driven and Pearson-Moskowitz were right and the fetch were very long, things would be lining up along here. However, you can see that most of the data here plotted against inverse wave age. So the inverse wave age is well below 1. So we have old oceans, old seas, or significant slope. And the significant slope, again, indicative of old seas, shows that we have a large scale, a wide variety of wave ages and wind conditions, but we don't have a whole lot of young seas. So that's something that probably is typical of many deep ocean sites, but may influence the geophysical model function as we go to these areas, because things like the significant slope, which can influence the slope modulation, will change for those seas. So with that caveat, we move on. So what do these geophysical model functions look like? And the way to look at them is to take a look at the radial velocity that's measured, subtract out the coincident radial velocity from the surface instruments, and bin it into bins. And here I show 9-degree bins in azimuth. So 0 here is you're looking along the wind direction, the downwind direction. 180 is you're looking along the upwind direction. And so you can see several things. One of them, we have 3 kinds of ground truth here: surface drifts, ADCP, and DOPVIS. And they basically follow a very, very similar pattern. For the sake of illustration, I've fit curves using the geophysical model function to that, to each one of those. And you can see that they have pretty good agreement. But there are places where the data are not constraining the geophysical model function, where they give you data that are pretty suspect. So we have, this is our distribution of data as a function of wind speed and as a function of platform. So you can see we have a fair distribution of data between about 4 meters and maybe 8 meters, and less data after that. And because we collect very often along the wind direction and the assets are to our sides, sometimes we are missing the data in the upwind or downwind direction. So that is a limitation. So sorry about that. So you can see a good distribution in the upwind, downwind directions for up to maybe 7 meters per second. But after that, certainly DOPVIS start to drop off, and we shouldn't trust it too much. Shouldn't trust too much that this is here. This is only one day's worth of data, because DOPVIS collects a whole lot of data every swath. There's a lot more DOPVIS data in there, but it's only one day's worth, so we shouldn't read too much into that. Uh, so one of the things that to worry about is these platforms are measuring currents at different depths. The ADCPs are measuring 4-meter currents. The surface drifters are measuring 40-centimeter currents, and DOPVIS is measuring, at least in the measurement that I've taken from DOPVIS, an integrated thing that's between the surface current and a couple of meters. And so one of the questions is there significant shear or wind drift difference between the two of them? And one of the ways to look at that is to take a look at the components in that harmonic expansion. And, it's somewhat messy. The error bars are not small in some cases. But if you look at the dominant component, is the C1 component, which is on the order of 90 centimeters per second. All the other ones are on the order of below 10 centimeters per second. And so any differences that are going to pop up are in this dominant component. And also in the dominant component are where you would expect to see wind drift differences between the surface drifters and the ADCPs, or DOPVIS and the ADCPs. And so if we take a look at the difference in those fitting coefficients and the reference 4-meter ADCP velocities, we get something like this. We can plot it here as a function of wind speed, and this is the amplitude of that contribution. And you can see that it follows roughly a straight line curve, consistent with about a 1% wind drift. There's significant differences over here, but as I said, this is just 1 day's worth of data. Not sure we should read too much into that, but it's something to be investigated further. So in order to be consistent in comparing the currents and into training our models, what I've done is I've taken the 1% wind drift, which is consistent with some of the theories out there, some of the observations by Fabrice and others, and Roger Samuelson also has a theory that says wind drift should be in this order of magnitude. And we subtracted it from the data and tried to reference everything to 4-meter depths. Of course, the shear is not as simple as a straight 1% wind drift. So we expect to see some dispersion as we go away from that. But you see that the difference is not insubstantial, can be tens of centimeters per second. So we better subtract it if we want to get something consistent. So after doing that, we train everything on the entirety of the data, and we get your physical model functions, basically the amount of surface current that should be subtracted that look like this. So these are the fits that we have here, and they seem to show pretty good consistency. And just for historical reference, I've put in something called KDOP, which was the model function developed by Yurovsky using a limited data set in the Black Sea, and an additional geophysical model function that we developed at JPL using limited comparisons against a sensor that was operating the same principle as DOPVIS. And you can see that there are certainly differences at the lower wind speeds, but in the upwind and downwind differences, they're not too different from the historical one. The main differences are that the historical ones look very much like a sine wave, whereas the ones that we see now have a lot squarer distribution. And that, we speculate, is because of the distribution of bound capillary waves and gravity waves in the ocean. So there are substantial differences between what we see now and history, but not completely inconsistent. We can compare this against simple models that like the model. And those operate in something called the modulation transfer function. They assume that the brightness can be modulated, or the modulations can be modulated as a function of the phase, basically the phase of the large scale waves. And so if you start with a gravity wave that looks like this, you will have modulation due to the hydrodynamic modulation that will have something which is a component in phase with the U component of the wave, and something which is in phase with the W component of the wave. There will be modulation due to tilt, which is only in phase with the W component. And then the total thing will look something like this. And you can make these modulation transfer functions. And from our data, we can make it and compare against historical modulation transfer functions. So what we see here is this is a function of wind speed, is the real and imaginary part of that modulation transfer function. The black dots are our data. The historical data are data from various other observations. And you can see that it's not completely inconsistent. You can use that to apportion how much of this radial velocity is due to Bragg, free Bragg, to a tilt component, and to a geophysical model function, to a tilt and hydrodynamic modulation. And you can see that you can get pretty good agreement in the upwind, downwind velocities, and you can get a story as to which is contributing where. But what you do not get with a simple picture like this is this squarish distribution. And so we still need the real data to understand what's going on there. So having said that, how well does it work? So we subtract everything, the simple curve, the gold curve over here, from our radial velocity observations. We also have the wind direction and the wind speed from the scatterometer. So they are exactly coincident with the measurements. And we compare against all the in situ observations. And so on the left is how well things compare when you just you have the Doppler scat radial velocities after correction versus the in situ measurements, all of them bunched together. So they have a correlation coefficient of 0.93 and a standard deviation of about 12 centimeters per second. So we'll come back to that. And basically, it's an unbiased estimate. You can take a look and see how well this estimate aligns with the different wind speeds, whether there's an area where we work better at different wind speeds. And you can see a couple of things. First of all, as the wind speed increases, the correlation coefficient increases. So at low wind speeds, we have poorer correlation coefficients and noisier data. And that's because at low wind speeds, a lot of the waves that are generated are not necessarily generated by the wind, are not locally generated by the wind. And the backscatter cross-section is very low, and so things are noisier. But things improve with higher wind speeds, and overall, you have a pretty decent correlation. And in general, you have a pretty decent correlation, but the scatter is going up. You can separate this as a function of the different sensors. So this is versus the 4-meter ADCP, a correlation of about 0.87. The surface drifters plus the wind drift correction, correlation of about 0.85, and DOPVIS correlation of about 0.96, and better correlation. So DOPVIS is in some sense the closest thing to what we measure because it is reflecting the surface currents most closely than the other ones. The surface drifters, in order to get a velocity, what I've done is I've taken the GPS position measurements, average over 5 minutes, and fit a curve, fit a derivative through those. and feet of velocity, which is somewhat noisy process. So some of this dispersion may be also due to that. Some of the dispersion here may also be due to the fact that there's vertical shear in the currents, and so we're getting differences there. So to try to convince you that it's not all noise, because if you look at this, say, well, 12 centimeters per second, what am I going to be able to do with that? And the issue, or what I'm going to try to convince you, is that these 12 centimeters per second are really long wavelength systematic effects due to either geophysical model function or actual shear differences that have long wavelength signatures. So what I've plotted here is for all the days that we collected Doppler scat data during the intensive operation period. And I'm plotting in blue the kinetic energy spectra for wavelengths between 20 kilometers and 400 meters. And then I also take a look at the transverse component and the longitudinal component. I will not go into this. This is important for turbulence theory. I will just say that this indicates a high level in homogeneity for the submesoscales. And there's a very interesting story here. I'll talk about it with more physics later. But what I want you to take a look at is that the spectra going all the way down to 400 meters do not show any flattening out, as you would expect to see if you were dominated by noise. You can get a similar story from the structure function, basically the square difference of the velocity at two different points as a function of separation. And so I've looked at separations between 400 meters and about 20 kilometers in this case. You can see that the slopes of the structure functions are related to the slopes of the spectrum, and this is to be expected. We can talk about that later. But for the sake of this talk, the only thing that is important is, again, that if you look at the smallest separations, so basically these are the things that are supposed to be a function of the random noise. The contribution due to the Doppler scat signal is less than an order of about 5 centimeters per second or so. So these differences that we see between Doppler scat and the other sensors probably have some geophysical long wavelength signatures that still need to be further investigated. But to show you that they're not completely nonsense, I will just give you some basic pornography from the ESMO experiment. So we were lucky enough during part of ESMO to sample a developing ocean front. We had a frontogenesis event over here. We have wave-guided sail drones there. This is SST from Sentinel and chlorophyll. You can see the signatures there. And here are what Doppler scat surface currents saw as we headed into the development of this frontogenesis event. So this is over 3 days. We could observe the total surface currents, which we decomposed into a large-scale current and a small-scale current. Small-scale current indicative of the submesoscale, so you can see eddies developing and forming. We also get the winds, and we get the relative vorticity and the strain rate, and you can see high relative vorticity beginning to form and high strain rates, and these things eventually turn into this front that developed between October 23rd and 24th. So here I'm showing you the currents, the submesoscale filtered, high pass filtered currents from Dopvis as contour lines, and as a background, we have the wonderful SST data, high resolution SST data that was collected by Jerome Muhlenmaker for the Moses instrument that was flying at exactly the same coincident time. And you can see this beautiful relationship between the currents, the submesoscale currents, and the front as seen by the SST. You can also see that in the currents developing very quickly between October 23rd and 24th, some very large instabilities developing and then moving on as waves down the front. Also, if the data were incredibly noisy, we would not be able to compute things like relative vorticity. And here's a plot of the relative vorticity that we compute and the contours of the high pass surface current. So you can see it all makes some sense. And so there's hope for Doppler scatterometry in spite of needing to still understand things. And there's also wonderful signatures that you can see if you look at the coincident winds and currents. This is some analysis done by Alex Weintier for using the Doppler scatter winds, and you can see the estimated currents from our GMF, the wind curl, the wind divergence, and the current curl and the current divergence. They're supposed to be anti-correlated, and in fact they are. So somehow it's all coming together, making some physical sense, but compared to the 40-year-old geophysical model functions for scatterometry or for altimetry, we still have some development to go. And that's it. That's all I have for you to do there.
Thank you, Ernesto. I'm sure that people have questions, so I'll let people raise their hand or put questions in the chat. And while people are thinking, I guess I'm wondering about the, trying to figure out where I put my question, about the effects of swell and whether the results would be, that are coming out of S mode in one region of the California current would look really different if you were someplace that had a different background swell characteristic.
So during the month and a half, that month and a half was two different years of data collection. We collected a wide variety of surface conditions. And so if you take a look at the distribution of wave age, we don't have very young oceans, but we do have all this stuff is swell dominated. And we have swells that were coming from the north, the east, and the west. So we have swells from all sorts of different directions. I haven't shown you here, but I've looked at the residuals of the geophysical model functions against swell direction, against significant wave height, against wave age or inverse wave age, against significant slope. And at least with the amount of data that we have here, there's no clear signature.
So that's really interesting. I guess the really young seas would maybe require sampling in really stormy conditions and might yield something different.
Yeah.
I see that Tom has his hand up.
Ernesto, you mentioned that you think the relatively worst performance of the GMF at low wind speeds is basically due to the fact that it's old seas or non-local wave effects. I guess that could come into play in different physical ways, like changing the, differences in the wave field that affect the occurrence of bound harmonics or effects on the surface stress that play into your wind speed correction. Do you have any, what do you have in mind for the physics?
So yeah, the physics is actually quite interesting. a while ago, Bill Plant and others speculated that below a certain threshold wind speed, no free capillary waves or Bragg resonant waves would be generated for scatterometry. And that's been borne out. So typically what we expect is that the resonant capillary waves that are present are probably generated by the gravity waves that have longer wavelengths. And so my speculation is that for very low wind speeds, a lot of these signatures that we see from the capillary waves have a large bound capillary wave component. So they're bound by the longer waves, which are influenced by swell, but also influenced by older winds. So winds that may have been there earlier on and may have decreased at the time. But this is why collecting data on the spectra, such as the one that you can get from an optical Doppler polarimeter, so some of the things that Nathan Laxag or Chris Zappa have done will be invaluable to try to understand the physics of this. Of course, it's very hard to do in the deep ocean, and it's not something that we're set up to do with any of the systems that we have during ESMO.
Thanks. Fabrice has his hand up.
All right, thanks, Ernesto. I just wanted to, congratulate you and all the team for collecting the data and making, showing that it works. So it's really an impressive piece of work. And I think we're all humbled by the multi-scale physics, what happens. So I don't think it's going to be anytime soon that we understand everything. So I just wanted to comment that if we measure at lower incidence angles, which was the skin proposal, we think we understand a bit better the physics, but then the wave Doppler is actually much larger, the wave impact on the Doppler measurement. And so I guess that at these higher incidence angles, your GMF data shows that there's actually a not so strong variability due to presumably different sea states or just shear or many other effects. So I think it's very, very encouraging to show that, even if we don't understand everything, that things are there's some variability, but and hopefully we'll understand it better in the years to come, but it's not huge. And just one thing I wanted to ask you about the shape of the GMF and the choice of having this cosine expansion. I guess, we expect from, if we are just pure Bragg, we would have a top hat function or very close to a top hat function because you have one direction with more energy than the other. So the average of the two is just whatever direction that is, direction of the wind. And so instead of having just a sum of cosine, maybe you could just have a blur top hat or top hat plus some cosines. I don't know if you've ever thought about that, but just
I have. And in fact, there's an alternate GMF that I've developed using exactly the cosine theta over 2 to some power fit.
Right.
The fit is no better and no worse.
Okay.
So certainly when you look at things like this dip over here.
So the dip is true, or you're not sure?
Yeah, exactly.
Okay.
Is it true or not true? If you look at some of the Doppler only data, and so you can see the beginning of a dip being developing there. So I think that's an excellent question. One of the things that can give you a dip like that is the wind drift component. So you subtract cosine component to one of these top hats, and the wind drift component is substantial, and we don't expect it to be small necessarily, you will see a dip over there. And if you have something like a top hat and you subtract the cosine there, it does get something that looks like this. So my speculation, and again speculation, is that that dip is reflective of the difference in the current at the very top and the 4-meter depth that we used as a reference, and it reflects the wind drift. And the wind drift is consistent with this sort of 1% that you have there. Somewhat larger over here, and so that this is why the Doppler dips further over here. So you can see it going over there. But that dip seems to be potentially physically related to this wind drift. And it might not be there. We had true surface currents to compare against.
Thank you.
Thanks. There's a question in the chat from Anna Smoot, and I don't know if you want to unmute and ask Anna, or if I should read it.
I can ask it. So on one of your earlier slides, the title on it was current GMF estimation, and you listed a whole bunch of factors impacting the surface current measurements. I was wondering, are all of those factors you listed, are they currently accounted for in the Doppler scat data when you're getting the surface current estimates, or are those factors that you need to include in the future? Yeah.
These are all the physics, the minimum amount of physics that we know is there. There is some theory associated with all of them to some degree or other, but there may be other things. But right now, because we're taking a purely empirical approach, we say all this physics can be basically summarized as harmonic expansion. And it doesn't seem to be so far away from what the actual fits are. So if you actually take a look at what the data is, or what the data are, versus our harmonic fit, it's not too far away. So,
great.
I mean, it may be that the way to think about it is that this empirical function is a constraint on the modeling, as we try to understand this, as I tried to do here with the modulation transfer function, to try to understand where the physics are. So is it Bragg plus tilt? Is it Bragg plus modulation transfer function, hydrodynamic modulation transfer function? And you can see that using that simple theory, you can explain the upwind downwind differences pretty well, but you still cannot explain pretty well these differences at larger azimuth angles. So upwind and downwind we expect to be dominated by the vector components. Here on the sides, we expect to be dominated by waves that are at 45 degrees to the wind direction. So there's a lot of width of the gravity wave spectrum that comes in, and also for the capillary waves that are forced, there's a horseshoe shape for these gravity waves that force these capillary waves that can lead to something like this square shape up on the top. But you know, having been in the EM bias game and in the geophysical model function game and trying to model these things, after about 35 years of being beaten down, I realized that the days of big data are here, and big data has a lot of power. So we have, S-Mode has given us big data.
Great, thank you.
Rick Danielson has added in the chat another question. Do you want to ask that, Rick?
No, I'm not really sure there's any merit to it, but just I'm thinking freely again. If
for very steep waves, and so Rick's question is, you know, for very steep waves, like you would get in a significant wave breaking event, since you're looking from one direction, there's also the potential that you're shadowing a lot of what's going on. That's true. However, the significant slopes that we see in these cases is not incredibly large, and our incidence angle is 56 degrees. So we don't expect the shadowing to be very significant, but it could be if you go to much larger incidence angles. Having said that, let me just reply to something that Fabrice said. We have some additional data that I didn't have time to talk about, collected in a platform that vary as a function of incidence angle. And what we found is that this geophysical model function actually became simpler the larger the incidence angle became. So we went all the way to up to 65 degrees, and the correlation just went higher and higher with the incidence angle contribution. So not sure what the physics there is. I think it's because you're closer and closer to pure Bragg, but that's purely speculation.
Well, thanks. We have just a couple minutes left. I wondered if you could go back to the eye candy figures that you showed at the end. And I was really struck on this one in particular, that there are places where the currents and the SSTs look like they align beautifully, and there are places where they look like they align in very puzzling ways. And
well, so it's actually quite interesting how it developed. If you look at the small scale currents going into the front, to the SST front over here,
yeah,
you get a strong convergence, strong derivatives over here. And lo and behold, a day later, that's where the instability started to form. And so, it's not directly modulated by the SST, it's not reflecting of that. Is really reflecting on the convergence and divergence and the strain that is happening at the front that we're really measuring, and eventually leads to changes in the SST distribution.
You need the day of time for it all to emerge.
Yeah. This is the speed of these instabilities is something that I think we expected it to be fast. I'm not sure that the amount and the rapidity of this event was something that caught us all by surprise.
It's really impressive. Well, we are pretty much at the end of the hour. I see that Seth Zippel has his hand up, so why don't we take one more question?
Sorry to ask a question right before you're trying to close the meeting. I had a question about the 4-meter reference depth that you've been using. And it seems like it was sort of a convenient depth, but I'm wondering if I could see that very easily turning into a standard of something like the 10-meter wind reference height. And I'm curious if you've thought about if there's sort of like a ideal depth that you would reference if you had measurements at a certain height or something. I know there's all sorts of issues with defining the depth of a surface current measurement, but I'd be curious if you have thoughts on that.
I think that that is just a right-on question for this community. It's clear that what we're measuring is not the 4-meter depth. There's wind drift at the very least between what we measure, and there's the vertical shear that has been measured using various instruments. So if you wanted to say that the surface current is truth, then you could say something like Doppler at the shallowest depths would be the thing to use as a reference, as a standard reference, or something maybe like HF-Reder, which claims to measure a couple of meters depth. However, if you look at what most hydrodynamic models and what most models give you, they do not have an accurate representation of that top shear. And so if you want to make any sort of connection to what models are doing and to what things like drifters at 15-meter depth are doing, I think you have to make some sort of compromise. And I think like the 4-meter ADCP depth might be something that could be right in between the 15-meter of the drifter arrays and the surface currents of the Doppler. So But I think that should be a theme of discussion for this community.
Thank you.
Well, thanks very much. Thanks, Ernesto, for a great talk. And thanks everyone for sticking around.